Okay. So, Saima, today we'll be going to discuss the very important portion. Okay. Thus, in the previous class, we have discussed that the magnetic field lines, and there are some questions that is being asked on this topic that we're going to discuss today. Okay. Okay. Fleming left-hand rule. Today we're going to start the Fleming left-hand rule. And in the previous class, we have discussed the properties of magnetic field lines. So, what are the properties of magnetic field lines? That magnetic field line starts from North Pole and enters outside the magnet. It starts from North Pole and enters into the towards South Pole. Okay, moves towards South Pole. Okay, got it? Are you there?
Yes, sir.
Okay, so this is North Pole. Okay, they are moving from north towards south, and this is outside. This is outside the magnet. Okay, and we can say that inside the magnet, this moves from south to north. Okay, south to north. So inside the magnet, it is from south to north. Got it? It is from south to north. Understood? And it is actually, we can say that it is continuous. Magnetic field lines are continuous in nature. Means, like you see here, they are coming from north and they are entering into the south, and then they are moving from south to north. So they are inside and outside. So we can say that if I need to draw the magnetic field lines, so it is like this. Okay, and they are straight inside, and we can say that straight and parallel. They are in straight and parallel inside. Got it? They are straight and parallel inside, and we can say that uniform magnetic field. This is from North Pole and this is the South Pole, and we can say that inside it is uniform magnetic field. Okay, and outside, tell me, and outside it is, tell me, it is from south, it is from north to south. Okay, outside it is non-uniform. We can say that it is non-uniform outside. Okay, it is not uniform outside. Okay, got it? You understood?
Yes, sir.
Okay, so now moving to the next part is that properties of magnetic field lines. If I talk about the magnetic field lines, so the magnetic field lines is the area where the magnetic force can be experienced. Okay, its unit is Tesla. It is measured in Tesla. Or we can say that magnetic field has both magnitude and direction. Okay, it has magnetic field has both magnitude as well as direction. So we can say that magnetic field is vector quantity. Magnetic field is vector quantity. Okay, vector quantity. And magnetic fields can be described with the help of magnetic compass. The magnetic field, the needle of a magnetic compass is freely suspended in a bar magnet. Okay, so here we can have the characteristics. The characteristics are that the field lines arises from north to and into the south. We are talking it outside the magnet, outside the magnet. Okay, and the field lines are closed curves. Are closed curves. Why? Because why we are not saying? Because they are continuous. They are continuous. Okay, that's why we are calling them closed. Okay, field lines are closer in a stronger magnetic field. Got it? Field lines are closer in stronger magnetic field lines. For example, we can say that they will be more closer. For example, here we have North Pole and South Pole. So their field lines will be more closer. Okay, here, like you can see here, they will be more closer here. So we can say that strong magnetic fields are present at the poles. Okay, strong, got it? So here we can say that strong. So if they are closer, so closer in stronger magnetic fields. What does it mean? That magnetic field lines are closer in stronger. So where they are closer, the strong magnetic field is present. Okay, magnetic field is present. Present. Okay, we can say that field lines never intersect. Field lines never intersect each other as the two magnetic field lines means they never intersect each other. Why? Because if they intersect, then at the point of intersection, if you put the compass needle, it should point towards this direction as well as towards this direction. And it is not possible that they must there is a point or there is no points in the anywhere that a magnetic field magnetic needle is disturbing, okay, or getting disturbed, or we can say that it is pointing towards two direction. No, there is not a single point. Magnetic field never intersect each other as if for the two lines to intersect, there must be two north direction, means two north direction, which is not possible. Okay. So please note it down. Note these important characteristics of magnetic field lines because it is being asked in the examination. When you're done, please let me know. Okay. Done. Timer. Noted.
1 minute. Done, sir.
Okay. So let's move further. Next is this one. Here, these are the two more properties. Okay. So direction of magnetic field lines in a magnet is from south to north, and the relative strength of the magnetic field decreases. Means as the magnetic field lines as we move away from this one. Okay. Means we can say that the relative strength of magnetic field is shown by the degree of closeness. So if there is more means we can say that if the magnetic field lines are more closer to each other, so we can say that there is a stronger magnetic field lines is there. Okay. So note these 2 points also. Done? Noted?
Yes, sir.
Okay. Now, this closeness, or we can say that uh, this rule that how the magnetic field lines arises, or we can say that how the magnetic field lines look like around a straight current carrying conductor, it was given by the right hand thumb rule. Okay, so check in your copy in the previous class, do we have written this right hand thumb rule in your copy in the previous class?
Yes, sir.
We have written this one, na? Yes. So what does right hand thumb rule say? Straight, imagine that you are holding a current carrying conductor in your right hand such that your thumb point the direction of current carrying conductor. Okay, then you will, or we can say that uh, that imagine that you are holding a current conductor in your right hand and your thumb pointed direction of the current. Then your curl finger or wrapped finger will point the direction of magnetic field lines. Okay. Now this is very simple that you can see here that the current is going downward, and you can see here that if you are watching it from the top, okay, so you will watch it like this. They have been moving like this. So if your eye is here, okay, because you know that if I'm seeing anything here, okay, there's a two types of things that we need to understood here, that the things that you see. So for example, let's suppose this is a glass. Okay, let's suppose this is a glass. Okay, transparent glass. Okay, and if a person here, okay, so let you imagine here, for example, if I'm standing here, okay, and if I watch a clock here, okay, or anything that is rotating like a clockwise. So if I go, if this same is rotating like this way, but if I go behind the mirror, the thing, if I am seeing from here, I'm seeing watching it from here, okay, then if I'm watching that it is clockwise, it is moving like a clockwise direction, okay. Then if I watch it the same thing behind the glass, I will see that the same clock is anti-clockwise for me, anti-clockwise. Are you getting what I'm saying here? Are you
Yes, sir.
getting? So the simple thing is that if this is a glass, okay, if this is a glass, and if you are standing in front of the glass, and if you are watching anything that is moving clockwise, okay, like there's something like clock, okay, and if you watch behind the mirror, sorry, behind this glass, and if you watch the same rotating thing which is moving from here, if it is clockwise, it is moving. So when you move behind the mirror, sorry, behind this glass, you will find that this same rotation will be visible to you as anti-clockwise. Okay, as anti-clockwise. Got it? Got it? So
Yes,
if you
sir.
are if you are watching this one from here, okay, that, so you will find that this is like a, if you will see that it is clockwise. Imagine that there is a clock here, okay, and it is like this, okay, and it is moving like this. Okay, you can see here that if it is, okay, it is clockwise, its direction is, and you can observe here that how it is. So you can see that this is 6, then it is 9, and then it is coming 12 here, and this is 3 here. Okay, so this is 6, then 9, then 12, then 3. So it is clockwise. Okay, this rotation is clockwise. Then you can see if you are watching it from here, you will observe it is clockwise. Got it? Got it?
Yes, sir.
Okay, same thing if you watch it from this one, from here, and you watch it from towards upward, okay, then you will find that it will be considered as anti-clockwise. Okay, or in simple word, if I say that if the current is coming towards you, if the current is coming towards you, okay, if the current is coming towards you, towards you towards towards you, then then the direction of magnetic field lines will be, how it will be, tell me, Tell me. It will be, if it is coming towards you.
Anti-clockwise.
Yes, it will be anti-clockwise. It will be anti-clockwise. Okay. Anti-clockwise. Got it? Understood? And if it is going away from you, for example, if you are watching from here and you are watching from this position, the current is coming towards you. So first for you, the current will be anti-clockwise. Okay. It will be anti-clockwise. It will be anti-clockwise and you will watch it like this. Okay. But if you watch the same thing from here, the current is going away from you and this same thing will be observed to you as a clockwise. When you watch it, you will 3, 9. So you will watch it here. Okay. So if you are watching this one here, so and the clock is here, so you will find that this is 3 here and this is 9 here. Okay. And this is 12 and this is 6. If you are watching from here. Okay. And if you watch the same thing. So this is anti-clockwise. Okay. The direction is, this is 3, this is 9, this is 12, and this is 6. So it will be anti-clockwise. And if you watch the same thing from here, so when you watch it, so for you, this will be 3, because if you are having here and you imagine that there is a wall in front of you, this will be 3 here, this will be 9 here, this will be 12 here, this will be 6 here. And the direction is 9, 12, 3. So it will be, tell me, if it is, if it is going away from you, it will be clockwise. Okay. From 9, then it comes 12, then 3, then 6. Okay. Got it? From 6, it goes the second since. Okay. The clock moves. So if you are watching from here, it will be 3 here, 9 here, 12 here. Okay. And if you are watching from here, then it will be 9 here, 3 here. Okay. You can consider yourself. Okay. Got it? So depending on the side that you are watching, in simple word, if the current is coming towards you, then it will be considered as anti-clockwise direction. And if the current is coming, or we can say that is going away from you. If the current is going going away from you, then tell me what? If the current is going away from you, then
The magnetic field is clockwise.
yes, away, then the magnetic field will be clockwise. Got it? Magnetic field will be clockwise. So you have to note these 2 points. Got it? Moreover, uh, for example, let's suppose if I'm having this, and if I'm saying that you are watching it from the top, okay, like this, and you find this like this, there's a question for you, and the current and the magnetic field lines is just like this, okay? So can you tell me that is the current is moving from top to, means is the current is coming towards you? You are watching it from here. So can you tell me that is the current is towards you or away from you? Or means
It's
if it is
towards
like
me.
this, it's towards you, okay? So why? Because it is anti-clockwise. So you are watching from the top, okay? And you watch, if you watch it from the top, so it is anti-clockwise direction, that it will be towards you, okay? And you know that the direction of current, the, direct, the direction of current is always taken as the direction of electron, the direction of proton, or the opposite to the direction of opposite to the direction of electrons. Okay, so many a times it has been given in the question that if an electron is projected from north to south, okay, so we have to take the direction of current as from south to north. Okay, got it? Got it? You understood?
Yes, sir.
Or should I note it down again for you? Because we in the previous class we have discussed this one. Tell me, should I write it again?
No need, sir.
No need. Okay. So if I talk about this one, that here we have a question. Okay, this we have done. Okay. Now, if you talk about the magnetic field lines due to, you can check it here. It is in the form of concentric circles. Okay. And here you can see that here that for every point, if the current is going towards you, away from you, if you watch it from here, so it is going away from you, so it will be clockwise. So direction of current will be like this. Got it? Got it? It will be clockwise
Yes,
because it
sir.
is coming downwards. Okay. And if it is like this, then it will be like this. Direction of current. So it can be represented by the concentric circles. In every point, a circle become larger as we go away from it. Okay. Every point on the wire, current carrying conductor, or we can say that every point on wire, current would rise. Means we can say that if you means every point on the wire means everywhere. If you can't imagine that this is the only point where the magnetic field lines will be there. No, if you put it here will be also the magnetic field lines. So every point will be considered as means if at every point we can have the magnetic field lines happening. Okay, and we will say that this current carrying conductor will be considered as loop. Okay, the direction of magnetic field lines inside the loop is same. Okay, got it? So please note these points also. Magnetic field due to current through a circular loop. Okay. So let me explain just a minute. Just a minute. Magnetic field due to circular loop or current carrying conductor. Current carrying conductor. Okay. So let me explain you this one. This was a straight line diagram that I was just explaining actually. Okay, so let me explain you. The magnetic field due to a circular current carrying conductor. So if I talk about this one, let I'm having a this one. Okay, this is a table. Imagine this is a table. Okay, and here we have a hole here, and here we have another hole. And if it is coming like this, if the loop is, this is a circular loop. Okay, got it? And inside this was is a wire that would be coming like this here, and this will be coming like this. And we just connected this one positive terminal, and this one we have connected with negative terminal. Okay, got it? Got it?
Yes.
So if I talk about this one here, this is the magnetic field lines. Okay, here like this, because this is the wire. For a point, we can consider this as a straight wire. Okay. In the middle of this one, it is a straight line. Got it? So you know that wire, the direction of current is from positive to negative terminal. So it will be moving like this. Got it? Got it? Now,
Yes, sir.
can you tell me the direction of this one? Direction of magnetic field lines in this loop here. Will it be clockwise or anti-clockwise here in this one, in this loop?
Anti-clockwise.
Yes, it will be anti-clockwise because you are watching it and the current in this loop is coming towards you. So it will be anti-clockwise. Okay. Anti-clockwise in this direction. Okay. And if I talk about this one here of this one, it will be clockwise or
Clockwise.
anti-clockwise? Yes, it will because it is going away from you. So away from you means you are watching from this side and it will be anti-clockwise. Okay. Sorry, clockwise. Sorry. So it will be like this. Okay. It would be like this. Got it? You understood?
Yes, sir.
Now, what you need to understood here uh is that okay, this is positive and it is moving like this. Okay. And what you need to understood here is that this is the inside portion. This is the inside portion of the magnetic loop. Okay. Or we can say the current carrying loop. And this is the outside direction of the current carrying loop. This is the outside direction of the current carrying loop. Okay. Got it? This is the outside direction. Okay. So inside you can see that inside the loop, the direction is same. And outside the loop, both the direction is same. You can say, but it is opposite, but same. Okay. Got it? Here it is coming downwards and it is also coming downwards. Okay. And you know that if this is a circular coil, okay, like we are imagining that this is a circular coil like this. Okay. And the magnetic field lines are moving from here like this. They are entering into this like this. They are just making the close curved, but they are entering like this. Okay. They are just entering like this. They are just making close curve. Okay. But they are entering like this. So can you tell me that which pole, if the current is moving like this? Okay. So here on this side of this my screen. Okay. That I'm saying that this is, let me explain you with the help of this 3D pole. Okay. So and if I ask you here, okay, so you can imagine that this coil is in the plane like this. Okay, in the plane like this, or we can say here it could be like this. Okay, on this side, on this side, on this face, will it be the south pole or the north pole? On this side, I'm just facing. You can imagine that on in front of you on the screen, will this be a south pole, or inside the screen, will it be the south pole or north pole? Which pole it is? So you can see here that the
North
magnetic
Pole.
field lines here on this on towards your sides. Towards your side, will it be the south pole or north pole? Towards. If it is circular, just imagine that this circle is on your screen and the magnetic field lines are entering. So you can check it like this way, that this is the bar magnet, okay? And inside the bar magnet, the magnetic field lines moves like this from south to north pole. They move from south to north pole, okay? Got it? So if the inside the bar magnet, if the magnetic field lines, you know that they are moving away from you, means we can say that this side where you are facing, this side is the south pole, okay? South pole. And the another sides where you are not facing, this is the north pole. North pole. Why? Because inside the magnet, because this is the inside region. This is the inside region. Inside region of magnet. Of magnet. Okay. Got it? And this is the outside region. We can say this is the outside region of the magnet. So we can see here that this is moving from south to north. Okay. Got it?
Yes,
Got
sir.
it? So we can consider it as like this, that this is the north pole since they are moving and it is coming towards you. Okay. So they are moving away from you. So this is the south pole. And if it is coming towards you, then it is the north pole. Got it? If the magnetic field lines is coming, these are simple things. We can say here that if you see the current, now if I'm having you, this is a circular coil, and if the current is seeing that if the current you see in the coil is clockwise or anti-clockwise, tell me. Is it clockwise or anti-clockwise? The current towards you. It is clockwise, na?
Clockwise.
So you can see that this clock is can be, you can consider this one. This is the clockwise direction. So if the current is clockwise, then the pole will be, so we can say that pole, magnetic pole, magnetic pole. And this is the, okay, got it? You understood? And it is magnetic pole. Understood?
Yes, sir.
Okay. And this is the south pole if the current, direction of current is clockwise. Clockwise, direction of current is clockwise. Got it? And if I talk about this one, if it is, if you are watching this one, the same coil from the other side, you will find that this direction will be considered as the means the same current direction will be considered as means anti-clockwise. You will see that the same direction, if you see it from the screen, behind the screen, you will see that if it is 3 here, then means okay, here if it is clockwise, then it will be anti-clockwise from the other side. So if it is anti-clockwise, if you see the direction of the current is anti-clockwise, okay, then it is the north pole. Okay, so the direction of current is anti-clockwise, clockwise. Okay, then the direction of current will be, you can say this is the direction of current, direction of current. Or you can say that if the magnetic field lines is coming towards you, then it is north pole. And if it is coming inside the magnet we are talking about, okay? Got it? Got
Yes,
it?
sir.
And moreover, you can understood it by the, you can keep reminded by this one, that inside the magnet, the magnetic field lines from move from north to south. And if someone asks you, then will the magnetic field lines will be uniform? Yes, it will be uniform. Okay, and they are parallel to each other inside this one. And this is, and at the between, we can say that there will be a straight magnetic field lines. Okay, the center. Again, because the curves are like this. Got it? You understood?
Yes, sir.
Okay, please copy this one. Done?
No, sir.
Note it down.
Done, sir.
Done. Okay. So let's move further. Now, now if I talk about the magnetic field due to a solenoid, okay, it is similar to that of okay, and we need to write some points here that also the factor affecting the what are the factor that are affecting the current carrying to the conductor, or we can say that circular conductor. So we can say that magnetic field, okay, magnetic field is directly proportional to the current. Okay, so we can write it here that what are the factors that are responsible and that affect the magnetic field of a circular current carrying conductor. So we can say that magnetic field is directly proportional to the current passing through the conductor. The more current, then there will be, okay. And magnetic field is inversely proportional to distance. If you are going away from the conductor, then the magnetic field will be, strength will be less, okay. And moreover, if the number of turns is more, okay, so we can say that magnetic field, we can say here, it is directly proportional to the number of turns. If there is more and more number of turns, then we will have more stronger the magnetic field, okay. Next one is magnetic field is additive property in nature. Means it is an additive property, i.e. magnetic field of one loop add up the magnetic field of the another loop. For example, if you have B magnetic field, okay, or, or 1 Tesla magnetic field, for the one coil. So if you are having 100 turns for the same, you will get 100 Tesla. Okay, so this we can say that this is because the current in each circle or circular turns has same direction. Okay, so please note these points also. This is important. Done.
No, sir.
Noted. Noted.
Done, sir.
Done. Okay. Now the magnetic field. We can say that magnetic field of a solenoid is similar to that of bar magnet. Okay, but what is the difference? You know that it is an electromagnet, so we can reverse the direction of the magnetic field by just changing the direction of the current. Okay, the strength of the magnetic field can be increased or decreased, okay, by changing the current number of turns. Okay, so V is equals to mu naught I. Okay, V is equals to mu n I. This is the B represent for the magnetic field here. Mu is the means we can say that it is the permittivity of magnetic field. Okay, and this is constant here. N is the number of turns, and I is the current. So we can say that magnetic field can be increased by increasing the number of turns and by increasing the current. And we can say that here that if it is moving away means outside the magnet, this is same that is a bar magnet. But if I talk about this one, that here you can imagine that, if I ask you that this is a solenoids. Okay, this is a solenoid here, and if the direction of current is given to you only, so can you tell me the magnetic which pole will it be considered? So this is like this. Okay, is the number of turns that are coming. Okay, and this is like this. So can you tell me that if this is the positive terminal and this one is like, okay, and we are just having this one, can you tell me that can you tell me that which direction the current it is going to have? Or sorry, can you tell me that which pole it is? Is it the North Pole or the South Pole? This pole is North Pole or the South Pole?
South Pole.
South Pole. So when you see here from this one, so you will okay. So you will find that the current is moving. Okay. So for this one, okay, you will find that the current is coming like this and it is going behind the bar magnet. So if you watch it like this, the current would be moving like this. Okay. It is going behind the magnet. Okay, like this. So you will find that it is going anti-clockwise. Here it is 3 and then it is okay. So you find that if the current is moving like this, so it will go like this. So it will be 3 and then it will go 12 and then it will go behind, that is 9. So if you watch it from here, imagine that there is a clock in front of you and you're watching from here. So you will find that this will be 3 on the, this will be your right hand side, and behind this one, behind the bar magnet, where the line is not shown here, it is 9 there. Okay, and it will be on the your left hand side. Okay, so you will find that the current is moving anti-clockwise. In this direction, the current is moving anti-clockwise. Okay, so it is anti-clockwise. The current direction is anti-clockwise. Then it will be the North Pole here. Okay, and this will be the South Pole here. Why? Because if you watch it from here, so you will find that this is 9 here, and if the current is going downward, okay, behind this one, this will be 3 here. Okay, so 9 3 6. Okay, got it. So this will be clockwise. The here from, if you watch it from here, it will be clockwise. Here if you watch it from here, it will be anti-clockwise. Are you getting my point?
Yes,
Are you
sir.
get? So that's why sometimes the direction of the coil may be given to you and will be asked that what is the pole, south pole or the north pole in the magnetic field lines here. So please here copy this one.
Done, sir.
Okay. Now you know that the difference between the electromagnet and the paramagnetic, their polarity can be reversed. Okay, just note it down. Just note the important points only. Just note the important points that you means the things that you are not aware. Okay, that this is temporary. This can be easily demagnetized. Okay, cannot be easily demagnetized. Okay, and we can say that strength can be varied by changing the current. Strength is fixed. Polarity can be reversed. Means the poles can be reversed. If it is not pole in an electromagnet, you can change the current. It will become the south pole. Okay, and generally strong magnet. It is a weak magnet. Not really. Done? Noted?
No, sir. Done, sir.
Okay. Next, moving towards the next part is, so let's have some questions here. Okay. First of all, this is a question from my side. Okay. Just have a question. This is do question number 9. Okay. So question number 9, read this question and then answer this one. This is important question and I'm going to explain you. Okay.
Sir, option B.
Option B. Okay. Let me check. Option B, no? Okay, let me check. Here it is. A constant current flows in a horizontal wire. You can see here. A constant current is flowing. Okay. The wire in the plane of the wire, in the plane of the paper from east to west direction. So imagine that this is the plane of the paper. Okay. And if this is the north position here, this is the south position here, this is the west position here, it is the east position. The current is flowing from east to west. So it is flowing from like this. And it is also shown here, the direction of the current. Okay. Got it? This is showing from east to west. And here the direction of the magnetic field at the point will be south to north. So it is asking from south to north. Sorry, not to south, not to south. So it is asking that will it be above the wire or below the wire. So you are saying just directly below the wire. Okay. So if it is going and if you are observing from anywhere, okay, just if you are observing from here, or you can observe from here. If you are observing here, the current is coming towards you, then direction should be anti-clockwise. If you watch it from here, then imagine that there is a clock in here and you are watching it like this. So if you are standing here, then there will be 9 here, this will be 3 here, this will be 12 here, because always on your right hand side is 3 and on your left hand side is 9. Okay, so just imagine that this is a anti-clockwise direction and this is the 3 here, this is the 12 here, this is the 9 here, and you are watching it from here. Okay, and this is 6. Clock is in front of you and it is asking this. Okay, and this is the above point and this is the below point of the paper. Okay, so if I ask you that anti-clockwise, because it is the current is going away from you, so it will be clockwise, so it will be moving like this. So this is the top portion, this will be the top portion, and this will be the below portion. So from north to south it will be below the wire. Okay, directly below the wire. It is, you are correct. Correct, absolutely correct. Okay, or you can imagine, or if you are facing any problem, so you can draw this 3D diagram like this. Okay, you can draw this 3D diagram, and if you draw this one, this will going to help you in finding the right suitable direction. Okay, just just draw this one like this way and draw x and y and z axis. Okay, so just this is the x z axis, this is the negative z axis, this is the positive y axis, and this is the negative y axis, and this is the x-axis, and this is the negative x-axis. Got it? Got it?
Yes, sir.
Now you need to understand here one thing, that if Now the current is it is east direction. Sorry, west direction. It is east direction. The current is moving, okay, from east to west. The current is moving like this. Okay. Now this is the north position and this is the south position. So it is asking now if you watch it from here, then it should be if current is going from you, that will be anti-clockwise. So it will be south to north above the wire, and below the wire it will be north to south. Okay, it will be north to south. You understood this one? So if in the question it is being asked, so below the wire, just below the wire, it will be south to north. Sorry, north to south. And above the wire, because this is the clockwise direction if you are watching it from here. Okay, got it? Understood this one?
Yes, sir.
Okay, next is uh so if this question, if I ask you this question, okay, here question number 3. Okay. Oh, I have not. Okay. And just do question number 3 here. Question number 3. Wait a minute. Do question number 3. Okay. Do this one and read the question first and then answer the question, which is the correct one.
Sir, option A.
Option A. Okay, let me check. We give you a circular loop placed in plane perpendicular to the wire. Perpendicular means actually half of the wire is coming out of means it is perpendicular to the plane of the wire. So you can imagine it like this way. Okay, if we consider that this is the plane of the paper. Okay, now consider that this is the plane of the paper. This is the plane of the paper. Okay, now this is just consider that this is the plane of the paper, and half of the wire is coming away from the paper, and half of the wire is inside the in this one. Okay, so you can consider anything. So here the question is being given to you that this circular that a circular loop plays in a perpendicular plane on the paper if you are talking about. Okay, and when the key is on, the current as seen move from A to B. So if you are considering that this is towards you, this is towards you, and this is away from you, so it is the current is moving from A to B. So it is moving like this. Okay, and it is coming. You can imagine that this is the positive terminal, so it will be moving like this, and it is the negative terminal. The current will be moving from negative to positive. Okay, got it? No, no, no. This is the positive terminal. Okay, and this is the negative terminal. So it is moving like this. So the current is moving like this. Okay. So you have to understood this one very, very thoroughly. Okay. Now we will consider that the current is moving from positive. It moves like this and it comes like this. Okay. So what we are seeing here is that here it is given that the current as seen from A. Okay, the current as seen from point A and B. Oh, I'm not. This the current direction is not given. I'm sorry for that. The current direction is not given. He's saying that current as seen from point A and B in the plane of the paper access to this one. Okay, we can consider from A and B. Okay, is anti-clockwise. Okay, okay, and clockwise respectively. Means if you watch it from A, it is anti-clockwise. Okay, and if you watch it from B, it is clockwise. Okay, so we can see here this from this position, we are just watching it clockwise, clockwise direction of the current, and from this position is anti-clockwise. Okay, A is anti-clockwise and B is clockwise. Okay, this is anti-clockwise. Got it? Or you can see here also if you watch it. So here this is 3. If you watch it from here, this is clockwise for here, na? This is 3. This should be 9, and this is 3. How it can be 3 here? If it is clockwise, na, so this should be 9. Yes, it should be 3. So it will be moving like this. Okay, you can imagine anyway. Okay, the magnetic field lines from point from B to A. Okay, the north pole is the resultant magnet. Okay, the north pole of the resultant magnet is on the face close to. Okay, so you can imagine that the side which is facing anti-clockwise direction, it will be going to have the north pole. Okay, north pole. No need to look at this figure. It will be going to give you the. It is just creating confusion because it is not in the 3D. Okay, so we can simply say here that the face which is facing, so A point is facing towards anti-clockwise. Okay, and anti-clockwise is going to have the north pole. Okay, the magnetic field lines from B to A. Now it is asking the magnetic field lines B to A. So this is A point, this is B point. So magnetic field lines inside the coil. You know that